Welcome! In this lesson, we build an intuitive picture for how faults and folds develop in mountain belts, and how we simulate them numerically. We will compare explicit fault interfaces with emergent faults from plastic failure, then visualize how folds grow and how surface processes feed back on the system. There are two widely used strategies to represent faults in numerical models. One is explicit. We insert a discrete, sliding interface where slip is allowed and governed by a friction law or by a prescribed slip history. The second is emergent. We start with a continuous medium that obeys a failure criterion like a more Coulomb plastic law, and shear zones localize on their own where stresses exceed the yield strength. For the explicit interface, we can assign a friction law and compute slip. Think shear equals cohesion plus normal stress times tangent of friction angle. For the emergent case, we use a plastic yield criterion, and when it is met, strain localizes into a shear band that behaves like a fault. Let us compress the emergent block and watch a shear band appear. We push from both sides. Once the stress reaches the failure envelope, a narrow band develops at an angle. Multiple bands can form and interact as shortening continues. Next, folds. In layered rocks under compression, stiff layers prefer to buckle. We will draw 3 layers above a weak detachment. Apply compression. The layers bow into gentle anticlines and synclines. Wavelength depends on layer thickness and stiffness contrast, as classic buckle theory predicts. Folds can form differently depending on the weak layers. With a frictional decollement, thrust tips bend layers ahead of them, a fault propagation fold. With a very weak detachment, broad detachment folds appear without a through-going fault. Surface processes matter. Erosion lowers uplifts and can keep a thrust wedge near critical taper. Critical taper is the small angle between the top surface and the base of the wedge that the system tends to maintain. In practice, we often combine methods. Insert a known major thrust explicitly, while allowing smaller faults to emerge, or refine a localization band into an explicit interface later in the run. Modern numerical models reproduce key features of fold thrust belts, sequences of imbricate thrusts, realistic wedge taper, and fold wavelengths tied to layer thickness. Summary: explicit faults give control where structures are known, but cannot easily create new faults. Emergent faults self-organize under a failure law, but need resolution and softening to localize. Folds arise naturally from layered buckling and from fault-related bending, with wavelengths set by mechanics. Surface processes feedback by modifying wedge taper and load, influencing the timing and sequence of deformation. Thanks for watching. In the next lesson, we will build a simple sandbox-style numerical wedge and track thrust activation through time.